All right, now we're on to our first AP Physics C exclusive section. So again, how I did the workbook is most of it is shared between AP1 and AP-C, but of course there's a lot of calculus specific things that Physics C Mechanics does. So you'll know that it's a calculus section if there's a little C label instead of the regular section title. I think there's like 12 of these. So a little bit extra content for C Mechanics, although AP1 has fluids, so they each have something. So this really helps if you're sort of an AP1 student that's also taking the mechanics exam and need to know what extra stuff is on CMAC. So this is going to be our first sort of calculus introduction. I'm not really going to teach the calculus here. I'm just going to do the physics application. I'm assuming you're going to get that in your calc class, so the basics of derivatives and integrals. So I usually don't go through the actual calculus operations a lot, kind of take the power rule and things for granted. So the first sort of thing that calculus achieves for us is this idea of a limit. And one thing we can do with limits is we can use limits to take the slope of a curve at a specific point. Because what we can do is we said that if you're trying to find the speed at a certain moment in time, the best idea is to sort of think of taking like a high FPS video and then just take the speed on those little windows there. So that's essentially the idea behind a derivative, where essentially we can find the velocity at a certain time by taking the average speed, or average velocity rather, over a very, 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 very small time interval. So when you shrink that interval all the way to zero, it's just notation to change your deltas to just the letter D instead to represent that it is an instantaneous rate. So we can define velocity as the instantaneous rate of change of position, and we can define acceleration similarly as the instantaneous rate of change of velocity. Now, almost always we're going to be dealing with these quantities in one dimension at a time. So the x velocity is just the rate of change of the x coordinate, and the x acceleration is just the rate of change of the x velocity. And also, since velocity itself is a derivative, we denote acceleration as the second derivative of position with respect to time. So we'll start just with the classic. You're given a position function, and we are going to be asked a bunch of things. So the position in meters as a function of time t in seconds is given by this cubic polynomial. And we're going to want the velocity, the stopped times, the acceleration, and the zero acceleration times. So our fundamental relationship here is that since this is in 1D, we can just say the velocity is the rate of change of the position x with respect to t. So this object right here, dx dt, this is a noun. This is an object itself. But if you want to say take a derivative, we use the operator d dt. This instructs us that we are taking a derivative. It's minus. And now we apply the power rule. So this is the only time I'm going to state what that is. If you're just joining us, we haven't done that in calc yet. So the derivative, or to take the rate of change of a polynomial, this is the easiest rule we have. Where if you have an nth power, the rule for the derivative is bring the power down, decrease the exponent by 1. And that lives in front with all the coefficients also. So here, bring the power down. So for a cubic, t to the third here, we bring the power down and we decrease the 3 by 1 to make it a 2. And then same idea here, we bring down the 2, which multiplies by the 3 to get a 6. And 2 minus 1 is 1, so this is t to the 1. And 5 is technically 5t to the 0, so we bring down a 0, meaning 0 for that constant term. And also, since this is the slope, what is the slope of a constant, a horizontal line? Well, of course, it's 0. So when is the object stopped? Well, what does it mean to stop? Well, to be stopped, it means you have 0 instantaneous velocity. So all we have to do is set our expression equal to 0 for velocity. And of course, I wrote this, so it's going to be some sort of easy factoring and not the quadratic formula. So everybody has 3, and everybody has t. So if I take out 3t from the first term, I'm just left with t. And if I take out 3t from the second term, I'm left with minus 2. And this is just a product property. How can I make 3t equal to 0? Well, I just plug in 0. How can I make t minus 2 equal to 0? Well, it's just 2. So there's 2 times where the object is stopped, which makes sense because it is a quadratic. All right, what about the acceleration as a function of time? Well, we can just do the whole thing again because we just said v of t was 3t squared minus 6t. So acceleration is just going to be the derivative of velocity with respect to time. So we take the derivative of the quantity 3t squared minus 6t. So if I bring down the 2, 3 times 2 is 6t. That's going to be 6t to the 1. And then minus, bring down the 1, right? 6 times 1, 1. And 1 minus 1 is 0. So this is just minus 6. Again, how we can easily see that. What's the slope of negative 6t if that was a line? Well, it's just a line with slope negative 6. So this would be our acceleration function. All right, when is the acceleration 0? Well, this is about as explicit as you can get in what it's asking for. So we just set acceleration equal to 0. 6t minus 6 equals 0. And we can see that this would just happen at t equals 1 second. So this is a pretty standard, just basic power rule situation. This is definitely like an easy multiple choice is usually where these questions like to live. And also, if you're a Desmos pro, you could graph these and just look at slopes. But these are intended to just be done algebraically. All right, now I had to spice it up a bit. It's not just polynomials we'll deal with in this class. We can also have trig functions and exponentials. So this is one that, depending on what book you use, you might not have got there yet. So you might have done the power rule already, but you might not have dealt with trig functions. So if we just kind of preview this, we do have a position function. We want velocity, we want acceleration, and we want some questions about max speed and the relationship here. But we see this as a cosine. So here's some more rules. These are actually on the Physics C reference sheet, but you'll have these memorized eventually. So some facts for us is that the derivative of a cosine function is negative sine. Should move this over because I need some more space. Negative sine. And then the chain rule says whenever you have functions inside of functions, you always have to multiply by the derivative of whatever was inside. That'll make sense more from context. And then it's almost the same. It's almost the same for sine. For the derivative of sine is positive cosine times the derivative of side. So we will find these rules helpful for us along the way. I did this intentionally to introduce you to the actual rules that we use in physics most often. So 80% of the time, it is going to be a polynomial. 10% of the time, it's going to be trig, and then we'll deal with the third. All right, so we want velocity. Velocity is dx dt. So I'm going to take the derivative of x max cosine of, this is omega, lowercase omega is that Greek letter. So what does our derivative rule tell us here? Well, our derivative rule tells us derivative of cosine is negative sine of whatever we had times the derivative of the inside. So what is the derivative of omega t with respect to t? Well, that would just be a line with slope omega. So we call this the chain rule factor whenever you have to multiply by the derivative of the side. So what is the acceleration? Well, the acceleration, let's do it again. Why is there a negative? So I'm actually going to simplify a bit because omega is a constant and so is x max. I'm just going to group those together because those will not really affect anything. And our second rule says derivative of sine is just regular cosine and then multiply by the derivative of the inside. So negative x max and omega, those are constants. They just come along for the ride. Sine becomes positive cosine. Derivative of the inside is still omega. And this one I think we will simplify for using my foresight because I know we're actually going to need this function for something later. So this would be negative x max, and then omega times omega is omega squared, cosine of omega t. So you see there's some sort of like cycle happening, which is an important property of these trig functions. You'll see they repeat like every 4. It goes from sine to cosine to negative sine to negative cosine and back to sine. All right, what is the maximum speed of the object? Well, we know that speed is simply the magnitude of the velocity. And our velocity function was negative x max omega sine omega t. We get x max omega sine of omega t. And a nice property that we use a lot in physics is the fact that the sine functions, if we remember what the graph looks like, remember our graph of our trig functions. Oh, accidentally hit scroll. That's definitely not what that looks like. Look at our graph of our trig functions. Sine is trapped between +1 and -1. So what that means is if we want the maximum value of sine of anything, it's +1, and the minimum value is -1. So what's the biggest that this quantity could be? Well, this is always less than or equal to 1 in absolute value. So this means that the maximum speed is just going to be x max times omega. And from a similar argument, you could say that the max acceleration would be x max times omega squared, because we have this cosine function that's similarly bounded. All right, so now we're going to verify that this property holds. This seems quite random for me to include, but this actually is really important for like one of the last things we do in this class. A motion is very special if it has this property. Uh, it has lots of nice properties that we'll explore much later, but I just thought this would be a little interesting thing to show, where the acceleration is actually directly proportional to the negative of the position. So our function for acceleration was this. And now we can just do some grouping to try to turn this into a position function. So the position function was x max cosine omega t. So we can do some rearranging to get that. So I can put a negative in front. I can keep omega squared in front. And then notice I can put x max cosine of omega t in a box right there. And we get the desired results. Because the boxed expression is just x of t. So we have showed that for this trig function type motion, the acceleration is proportional to the negative of the position. So that is I call this like going forward, where we just take rates of change. There's not much more you could be asked kinematics wise of just doing this. Now, we could also go the other way. And if you're taking calculus concurrently, you probably have not seen the other operation yet, which is called integration. So if differentiation is the slope at a point, integration is going backwards, meaning how can we get back to the original if we just have the slopes? So since slopes are rates of change, you can think of if you add up all of the rates of change multiplied by the time interval, you get the total change. So this fancy symbol is our integration symbol, and you can think of it as an S for a sum, because what integrals are sums. You are adding up something, some sort of rate of change or little pieces. So here, velocity times time represents a displacement, right? Because distance equals speed times time. So if you add up all the little velocity times time segments, you get the total displacement. And it's not distance because this could be negative. You could be going forwards and backwards. So this will tell you the net change in position. And similarly, since acceleration is the rate of velocity change, if you add up all your little velocity changes, you get the total velocity change. And these are our bounds, which just tell us where we begin adding and end adding. So we will use the power rule once again for this, where for the definite integral of a polynomial, we said the derivative operation, you bring down the power, decrease the exponent by 1. So we have to play the opposite game for the opposite operation, where we increase the power by 1 and divide by the new exponent. And we also denote that we go from A to B, where we take like a delta, where we subtract the bottom limit from the upper limit. Again, I am just giving you a speed run of this. You will cover this in your calculus. Now, since the derivative is a slope, all that tells you about your original function is how it changes. We actually know nothing about where we begin. So we'll often need some sort of initial condition to plug in on one of these sides to figure out exactly where we begin. So we'll kind of show what that is. All right, the velocity of an object is given by v of t equals 12t squared, where we have meters per second and seconds are usual units here. All right, first we want acceleration. Well, this is just going forwards, right? Acceleration is the rate. So acceleration is dv dt. So I am taking the derivative of 12t squared with respect to t. Bring down the 2, makes it 12 and 2, which makes 24. T after I subtract 1 from the exponent, and that's it. What's the displacement between t equals 0 and t equals 2? So this is the key difference between a derivative and an integral. So for an integral, it's about accumulating. It's about addition of many, many things between 2 points, whereas the derivative is a local sort of at one point idea. So anytime you're seeing between, those are going to be integration bounds. So an object's net displacement would be delta x is given by the integral of v dt. Because if you add up all your little displacements, you get the total displacement. So we're going from 0 to 2 seconds. Our velocity function was 12t squared dt. And what we have to ask ourselves is, since integration and derivatives, and differentiation rather, are inverse operations, we are just asking ourselves the derivative of what would give me 12t squared. Now, I did present you this power rule idea that we could just plug and chug. But again, you could think about it. So we know that if I take the derivative of a cubic, I get a quadratic. So we know there's some sort of power there of 3, but then we know that I'd also have to bring that 3 down at some point. So we could see that this would be 4t cubed, because just check by differentiation, where if I bring down that 3, it does give me the 12. Now, of course, like the more formal way of doing it would be it's 12t cubed divided by the new power, and it is the 4 that we expect. So now we do our upper and lower bounds, which means we have to plug in because we're taking a big delta. So you can think of what we found as like the accumulation function, which is how much has accumulated at a certain point. So if we want the delta, we want the amount that has accumulated after 2 seconds minus the amount that has accumulated after 0 seconds. And that gets us the overall change. So let's see, am I weak? Do I have to use the calculator? No, I don't think so. 4 times 2 cubed is 8 gets me 32 meters. And the other term is 0. We love when the initial term is 0. So now we can take this one step further and write a function for where is the object as a function of time. So not just how far did I go between 0 and 2, but how can I get it to work for anything? So we already found that delta x between any 2 points as a function of time is 4t cubed. So there are multiple ways of doing this. I like, for physics, actually expanding the delta. Because what is delta x? Delta x is where am I now versus where did I start? And that's going to be equal to 4t cubed. But here we're saying the object is at x equals 0 at 0, so goodbye by t equals 0 term. So I just get x equals 4t cubed. So I know that works, right? Because if I plug in 0, I get 0, and I know the function has to be 4t cubed. And now you can probably guess what this is going to turn into if we want just to change the initial position. You can guess how I have to shift this to make it work. But again, just to show you formally, delta is final position minus starting position, and that's equal to my displacement. And this time we're saying x of 0 is 5, so x minus 5 is equal to 4t cubed. Or you see this essentially is just a different y-intercept. Again, the slope tells you nothing about the y-intercept, so we needed some extra info to determine that. Let's see, am I doing squares or boxes? Or boxes or circles? Looks like circles. Let's keep it consistent. All right, so that is your standard integration problem. All right, now we'll do it twice. So just like we can integrate velocity to get position, we can integrate acceleration to get velocity, and then we could do it again. So we're going to look at a very special case of accelerated motion. That's actually the most common type of motion in this class, where acceleration is actually just constant. So our conditions here is that the acceleration is equal to a constant, and we're also just given the velocity at 0 and the position. So this is going to give us the general solution to just this uniform acceleration. And we'll see this equation come up a lot. We'll prove it without calculus in a later section, but it's a pretty important exercise. All right, so we want to find the velocity given acceleration. So we said that delta v would be the accumulation of all the velocity changes. So in our case, our velocity is changing between 0 and some time t that we're interested in. Our acceleration function is just a constant a with respect to t. And if we do this, we would get our delta v is equal to, well, if the rate of change is a constant a, that means our function would just be a times t. right? Because the slope of that would be constant, just a. And we're evaluating that from 0 to t. And similarly, for our delta v, we're beginning at some velocity v0 and ending at some velocity v. So we can actually just show the subtraction here. So we'd get our velocity minus v0 equals at minus a times 0, or velocity is at plus v0. And that should look interesting, because the next part says, how could we have deduced that this was linear without using calculus, and how do these numbers make sense? Well, we said that acceleration, which is the derivative of velocity, which is the slope of v, was equal to a constant. So what this means is, since slope of v is constant, v of t is linear. So that's all we are trying to get at here. So we could have reasoned that this should be a linear function for velocity, because if velocity is always increasing by the same amount every second, well, that's exactly what a line is. And notice it is plus v0, that's your y-intercept, because our velocity could start anywhere and still increase by the same amount or decrease by the same amount every second. Now let's do it again. So this one is more non-trivial. Like, it is possible with zero calculus, you could have deduced that at plus v0 does give the velocity, but this is a much harder thing without calculus. So we know that delta x would be the accumulation of all of the little displacements, v dt. Our velocity function was at plus v0, and we're just doing the same idea. So we're taking the change in position between our starting value and ending value, and doing our antiderivative here. We will just use the power rule on this one. Power rule says bump up the power by 1, divide by the new power. Same idea here, right? Bump the power up by 1, 0 goes to 1, divide by the new power. And we're evaluating that from 0 to t. So if we do that, we get x minus x0 is equal to 1/2 at squared plus v0t minus 0. So we could just add the x0 to both sides and get x equals 1/2 at squared plus v0t plus x0. So definitely a more complicated function for x of t. But apparently this should be expected. We're wanting to justify why this expression for x is quadratic under constant acceleration. So once again, it's this idea of the power rule. So we said that acceleration is two derivatives of x of t, which is constant. So this must mean we need a constant function after two power rules. And we know that that's going to be a quadratic. So let's explain that a bit more. So we know that if you take two derivatives of the position, it must be constant. And for that to work, that means eventually you must be out of powers after two derivatives happen. So if you start from a t squared, then you're going to get to 2t, then you're going to get to 2. So see that after two derivatives of a quadratic, we get to a constant. So that's how you could have figured that out. So if instead of constant acceleration, you had acceleration that was linear, well, then you'd end up with a cubic. So we can just realize that it's sort of 2 powers away. So this is less straightforward, I think, than the others, but this is a important result to do. All right, and last, here's our final function we need to know how to deal with in this class. It's exponentials. Now, we'll come back to these later, but the exponential is actually a really nice derivative rule where the derivative of an exponential is just the exponential itself times the derivative of whatever's in the exponent, just like we did with the trig function. And you know what? I've been making this blue. So let's keep that. So our exponential function actually has this nice property that it is its own derivative up to whatever the exponent derivative is. So we have a crate. Its velocity is given by this function, where v0 and c are positive constants. So it should help us to remember what this actually looks like. So let's see, do I make you graph it? No, I don't. So what this actually looks like is this would be a velocity time function that starts at some initial velocity v0 and then decays. So this represents exponential decay. All right, so what is the acceleration? Well, we'll apply our new derivative rule. Acceleration is still the derivative of velocity. So d dt of v0 e to the negative ct. v0 is just a constant, and then our exponential rule just says the derivative of an exponential is the exponential itself times the derivative of that exponent, so I need a negative c. So this means we would get negative cv0 e to the negative ct is our acceleration. Which means that our acceleration is actually negative and decaying with time, which makes sense, right? This is a negative slope, and the negative slope is getting shallower and shallower. So what would be the distance traveled by the crate after a long time? Well, we know that distance is going to be displacement in this case because there's no turning around. So we are just going to integrate our velocity function. And now we have to think about what are our limits going to be. So this is something that we do a lot in physics, where we talk about limits and limiting cases. So it should be pretty reasonable that we're going to start at 0, right? Because the crate is moving at 0. But what does it mean after a long time? Well, long time means look what happens at the longest time imaginable, which would be infinity. So we're going to look at sort of the limit where the final time approaches infinity. Now, your math teacher does not like you putting infinity in the integral sign, but this is physics class, and so we will. We will literally be plugging in infinity as a limit, and in this class, the infinity limit usually just sends something to 0. You have to be more precise in your math class, but it's physics. We're using it as a tool. All right, so our delta x is going to be, well, if we said the derivative rule was the function times the derivative of the inside, then the integration rule should be the function itself divided by the antiderivative of the inside, for this constant at least. This doesn't always work, but I would just recommend actually checking this in reverse. So I would get v0 e to the negative ct divided by negative c. So we can check by just differentiation. Again, I think that's often just a better strategy than memorizing integration rules, is trying to think, what is this function the derivative of? So who can I take a derivative of to get this object in purple? Well, we know it needs a v0. We know it needs an e to the negative ct, but we know that we'd have to account for this extra negative c so that when we use the chain rule, it cancels out. All right, so now we can factor out v0 over c. And if I plug in my upper limit, I would get e to the negative infinity minus e to the negative 0, or just e to the 0. And now we got to think about this. This might look scary, but again, just picture a graph. We know that if you plug in just a positive exponent, an exponential gets bigger and bigger and bigger. So if you're dividing by that, it's getting smaller and smaller and smaller and smaller, right? Because negative infinity is the same thing as 1 over e to the infinity. So we're dividing by a super, super big number, so we're going to get out 0. So this would be 0, and anything to the 0 power is 1. So we just get, out of all that, just v0 divided by c. And our value is positive, because I am going a positive distance. So now it says if the value of c is increased, the distance traveled by the crate after a long time decreases. So we will justify this claim qualitatively, meaning without math, and then we will justify it using the expression from part B. Now, this is my personal life hack where if you can't figure it out for the qualitative, just do the quantitative first. So this is quite simple using the expression from part B, because we said delta x was just equal to v0 over c, and c is in the denominator. So we can see that as c increases, v0 over c is going to decrease because I am increasing the denominator, meaning delta x decrease. You don't really need to say this in the future. Like, we accept the fact that you understand that denominator means an inverse relationship, but this is sort of what we're going for here. So how could we have figured this out qualitatively? So what does the c represent? Well, the c is this sort of decay constant inside the exponential. So this is the rate that the curve decays. And if you want to convince yourself that, definitely plot some of these in Desmos. So if you have a bigger value of c, what that does is we start at the same spot, but it decays quicker. So that's essentially the explanation, is if the value of c is increased, then the velocity function decays more quickly. So since v of t is decaying more quickly, the velocity is going to be smaller at all times for t greater than 0. So you're going to be traveling less distance per second at every single possible time, so you go a shorter total distance. So that resulted on you sort of knowing that this constant c is affecting the rate that the function decays. I thought it was interesting to ask, at least. So that is your kinematics with calculus. So I tried to make this like a mini calculus lesson, just to give you a speed run of kind of the operations. You will become much more comfortable, especially with the integration and the trig functions and the exponentials as time goes on. But that is just our sort of basics on how we can get the kinematics quantities from one another if we're given functions and have to do some calc with